Hello everybody. Once again I am here with you for the another session of the real gases and their behavior is to be there. And in the previous session we have seen a little bit about the thermometry, how to measure the temperatures in a different ways, and what exactly the relationships in between them and what are the differences as far as the minimum point and the maximum temperature measurements are to be there. Now this unit is quite interesting about the gas molecules behavior is to be there, and in smaller scale how the gas molecules is going to be behaving, that we will see in this unit. Basically we know there are three states. One is to be the solid, liquid and gaseous state is to be there. In general the smallest small part of the any solid is to be atom, that is to be well arranged in the solids, but it is a little bit loosely bonding in between them, and that's why we can say the liquid state is to be there. And definitely the gaseous state where the molecules are very much weak in their bonding, and that's why they are agitating or moving from here and there in the container, and that's why there is very loose bonding in between them. And what exactly in the real gases and their behavior in the previous part, real gases are considered to be as a will be forever in their state, but a little bit Andrews and Joule Thomson experiment a little bit given a different shape that about this concept, and that details we will see in this regarding the real gas behaviors are to be there. So let's start with this session, and today we will see Andrews experiment. So a little bit what I told you that as far as the gas behavior is to be as an totally we are learning in this unit, and as the gas states of the molecules are very loosely bonded, and that's why there is agitation moving of the gas molecule is to be there in the continuous way. म्हणजे गॅस मॉलिक्युल्स हे ॲजिटेशन तो एका जागी स्थिर कधीच नसतो, तो मूव्ह होत राहतो कंटिन्युअसली, अँड दॅट झिगझॅग मोडमध्ये तो मूव्ह होत राहतो पूर्ण कंटेनरमध्ये. आणि प्रिव्हियस नंबर ऑफ इयर्स लॉंग टाईमपर्यंत असं समजण्यात येत होतं की गॅस ही गॅस स्टेटमध्येच राहते कोणत्याही टेम्परेचरला, किंवा त्याच्यामध्ये काहीही फरक होत नाही. बट अँड्रूज एक्सपेरिमेंट अँड थॉम्सन्स एक्सपेरिमेंटनी बेसिकली द गॅसच्या बिहेवियरबद्दल किंवा गॅस मॉलिक्यूलच्या बिहेवियरबद्दल खूप चांगले एक्सपेरिमेंट केले, आणि त्यामुळे त्यांनी त्याच्याबद्दल जी काही स्टडी केली त्यावरून हे जे काही कन्सिडरेशन होतं की गॅस इज ऑलवेज इन द गॅस स्टेट, इट इज नॉट ट्रू. That with the different temperature and at with a specific pressure, there is a change in the gas molecule, or there is a change in the state of the gas to liquid, or there may be another way is to be there, and that details we will learn in this unit. And the first one is to be as an our Andrews experiment is to be there. So Andrews experiment is important because at the different temperature and the pressure, how the gas behavior is going to be changing, or the gas molecules behavior is going to be changing, that is to be shown by this Andrews experiment. And basically his work is totally on the carbon dioxide, CO2 is to be there. And in 1869 he studied this behavior of the CO2 with the pressure at the constant temperatures are to be there, and what at different temperatures what happens about the CO2 gas, and how the liquefaction takes place at a certain temperature level with the at below particular temperature, whether the pressure is going to be applied certain pressure, the CO2 gas is going to be liquefied, and that particular stage where the at that temperature where the gas is going to be liquefied, that is nothing but to be called a critical temperature is to be there. As we know, for passing any student we need 40% marks, that is the critical point for the your passing point is to be there. And that is what the either 40% marks means, you have to get 40% is your critical point. If you are not getting if you are getting below 40%, you are definitely failed. But if you are passing that level, that you will be your result will be passed. So likewise this critical point is to be there. Below this critical point at the temperature, below this critical temperature, the gas is going to be liquefied, and above that temperature either you are applying whatever be the pressure or whatever be the temperature is to be there, there is no change in its gaseous state. It will be remain as it is, but at a certain temperature and at particular pressure, below that temperature, these gases are converted into liquid state, and that is nothing but to be a critical temperature is to be there. And for a different gases, this critical temperature is going to be different. And let's see what is there for this Andrews experiment, and in detail we will see. Basically, important factor is Andrews experiment is based on the CO2 gas. And let's see what exactly the Andrews experiment setup is to be there. So this is what the very beautiful setup of this Andrews experiment. And what he has taken, basically the two glass tubes. At the top, these are capillary tube, and at the center it is looks like to be as an bubble and bulb like things. This is to be upper part, where I am showing you with the red lines. This upper part is to be capillary tube, and this is what the A and B, where I am showing the red lines, that is nothing but to be a bulb like glass tube is to be there. In between this there is a mercury for with the marking. These capillary tubes are with the scale, and that mercury is showing the pressure inside that particular glass tube is to be there. And here, this A glass tube and the B glass tube, if you look at this, A is containing air, and this B is containing to be as a CO2 gas. And that's what the experimental setup. Again, the important factor, this H type of the copper vessel is to be there. This is what the copper vessel is completely like a H shaped, and these glass tubes are inserted in this copper vessel. And this copper vessel containing also water bath, because it should not damage the things. That's why the water bath is going to be maintaining the temperature exactly as it is for the both the ट्यूब्स ए अँड बी. म्हणजे दोन्ही ग्लास ट्यूबला सारखंच टेम्परेचर राहावं, आणि त्या टेम्परेचरमुळे त्या ट्यूब्स फुटू नयेत, आणि त्याच्यामुळे हा वॉटर बॉथ तिथं यूज केलेला असतो. Lastly, at this bottom there is S type of the springers are to be there, which are to be screwed, we can say, and which are used for the piston type of the thing, where it if you are pressing it, or you are the pressure will be increased in the particular glass tube is to be there. And these both these plungers are to be kept at the same level, or the pressure is similar in that both the tubes, glass tubes are to be there. So this is what the experimental setup is to be there. And basically, at the beginning, how to insert the air and the CO2 gas. At the beginning stage, this is going to be a complete empty, that is to be your a glass tube, if suppose is to be there, it is completely empty, and the continuous air is passed through this other end where the red line it should be shown. The completely air is to be passed through this way, and for the 12-24 hours. And then afterwards the mercury is also going to be inserted for the pressure change, for the looking pressure inside it glass tube is to be there. And in another big glass tube, the CO2 gas is going to be inserted continuously for 24 hours, and then this going to be maintained in that fashion. So this is what the simply as an experimental setup is to be there about the Andrews experiment. This is all what we discussed about this, how this H-shaped copper vessel is to be there. Also the S are the stoppers which are going to be used for tuning. In this way it will increase the pressure inside the glass tube, and the pressure is measured in the capillary tube. Likewise the things are to be there, and volume of the A and the B are going to be maintained, and that is somehow the experimental setup is like this. And now what happens, or what to do exactly, the experimental point of view. As the A glass tube containing the air and the CO2 is to be inside the B glass tube is to be there. So pressure in the both the glass tube is going to be maintained corresponding to air and the CO2. Both the A and B glass tube are having the same pressure as far as the air A glass tube concerned, or the B glass tube is to be concerned. And now for the different temperature, the pressure can be varied with the help of the plunger, that is to be, yes, plungers are to be there at the bottom for the blows the glass tube. And the experiment is done while in for the different temperature, means maintaining the pressure constant, and the temperature is going to be varied in the systematic way. For the different temperature, the what happens for the CO2, what happens for the air, that is going to be maintained. And in this way, for the different temperature, what happens for the CO2 gas, what happens for the air, that is going to be calculated. And somehow for the different temperatures and the pressure, what the variation is there in between air and CO2, it is going to be measured and plotted on the graph. And what we have observed, that is shown here with this graph. And this graph is to be showing us what exactly the variation in between the volume and the pressure for the different temperatures are to be there. Means at the different temperatures from below temperature, that is 13.1 to onwards, how the variation in the pressure and the volume is to be there. So that is going to be calculated. Now what this is what the experimental setup, and what observations we have to do, that is to be also in front of us. Now let's see step by step what happens at the different temperatures. At the very first stage, that is at the 13.1 degrees centigrade, if you look at, there is a graph which is showing to be as an ABC. I am showing with the red lines, and the CD is to be there. So this is what the structure or the graph for this 13.1 degree centigrade. And here this scale is x-axis is with the volume, and the B is not where the pressure is along the y-axis is to be there. So if you look at this stage, where this AB portion is to be there, this AB portion is at 13.1, which is completely in the gaseous state. And from this B to C, this is what the stage where the uh, it is somehow showing clearly that it obeys the Boyle's law, and where the gas is going to be liquefied in this stage. And where C to D, it is completely in the liquid state is to be there. But what is it is happening, it is happening at 13.1 degrees centigrade. So this is what, as either you are at this stage, either this C to D, either whatever the pressure you are increasing, the volume will not be, means the pressure either you are going to be increasing, the volume will be not going to be changing at that stage. It will remain as it is, means it will start reducing, but at certain stage, once it is going to be one particular level, the volume will not change, and the pressure either you are increasing continuously, it will not affect to the volume is to be there. So this is what the stage where the 13.1 degrees centigrade, which is showing us that as it is mentioned in our observations are also to be there. That is 13.1 degrees centigrade, AB representing gaseous state. I already told you CO2 up to the point B. And in this portion, the gas is obeying the Boyle's law. BC, there is a decrease in the volume and slight increase in the pressure. This represents change in the state of the gas and gas to liquid. And at the C, whole gas is going to be liquefied, and the part C to D representing liquid state of the gas, I already told you. And either there is no change as far as this part is to be there. So if you look at the important factor I want to tell you regarding this variation, this C to D, the sorry B to C, it is to be liquefaction, or the Boyle's law is going to be obeyed, but liquefaction started, and this C to D is completely liquefied gas is to be there. So at the another stage, when the temperature is going to be increasing, that is what at 21.5 degrees centigrade is to be there. Above this temperature, above the 13.1, what happens if you look at this is shown with the FG part is to be there. This portion of the liquefaction of the gas is going to be reduced as the temperature is increased from 13.1 degree to 21.5 degree centigrade is to be there. Again, this G2H is completely liquefied stage is to be there. So as the temperature is going on increasing, this portion of liquefaction of the gas is going to be decreasing and decreasing. And the time will come at the 13.1 degrees centigrade as far as the CO2 gas is going to be concerned. There is a one point P where this is to be at that point, means above that point there will be no liquefaction of the gas is to be there. That means below this 13.1 degrees centigrade there will be a liquefaction of a gas of CO2 gas. That means 13.1 degrees centigrade, that P point is nothing but a critical point where the temperature whatever it may be, or 13.1 degree centigrade is the critical temperature, we can say. Why it is to be called as a critical temperature? Because below this temperature the gas is going to be liquefied, and above that temperature the gas is not going to be liquefied. Either you are whatever you are increasing the pressure is to be there, but at the below this 13.1 degree centigrade, as far as CO2 gas is going to be concerned, the gas is going to be liquefied, and that's why this 13.1 degree centigrade is nothing but to be a critical temperature, or the critical point is to be there. So this is what the case where we have seen. And above that means above this temperature, either whatever the temperature increase above the 31.1 degree centigrade, if you look at this 32.5, 35.5, or 48.1 is to be there, the gas is not going to be liquefied, it is going to be continuously in the gaseous state. Either you are increasing the pressure or the temperature, it is not going to be affecting. Below the 31.1 degree centigrade the gas is going to be liquefied, and that's why it is called the critical temperature is to be there. Above that temperature it may be obeying the Boyle's law, but there is no liquefaction of the gas is to be there, and that's why it is called to be as an 13.1 degree centigrade is the critical temperature point is to be there. So this is what the observations for Andrews experiment as far as the CO2 gas is going to be concerned. Now the conclusion part, where we are very much clear what we have learned in this Andrews experiment, that Andrews concluded with that CO2 can be liquefied by the application of the pressure, provided its temperature is 13.1 degrees centigrade. It is to be very much important, and this temperature is called your critical temperature, and that's why the temperature below which the gas can be liquefied, it is called as a critical temperature is to be there. And above the critical pressure the gas cannot be liquefied above that temperature is to be there. So this is what the case where it is to be clear from these observations. Another one, the whatever be the pressure, whatever the pressure at which the gas is going to be liquefied below the 13.1 degree centigrade, that particular pressure is nothing but to be your critical pressure it is to be there. And definitely the volume at that stage, it is nothing but to be called your critical volume is to be there. And the temperature, no doubt it is critical temperature at that point is to be there. It is the again the critical pressure part is to be there. It is the pressure applied on the gas at the critical temperature so that the gas can be liquefied. And again the as far as the critical volume, it is nothing but to be volume at um, volume of the gas at the critical pressure and the critical temperature is to be there. That means at the critical point, the whatever be the volume, it is critical volume, whatever be the pressure, it is to be critical pressure, and the temperature is critical temperature is to be there. So these are the points where above which either the gas is not going to be liquefied, and that's why these are nothing but to be a critical temperature or the critical constants we can call. So this is about the Andrews experiment, and results clearly indicating that the horizontal portion, either it is BC or the FG is to be there. The horizontal portion shows that there is a physical restriction uh, distinction between the gaseous and the liquid state, that gas is going to be converted into liquid. Again, second one conclusion or the result is that all the gases can be liquefied by the application of the pressure provided the temperature is below critical temperature. That is very important. And another, the critical temperature for the different gases are the different. As far as examples are to be given here, if you look at this stage where the oxygen is having the it is critical oxygen is having the critical temperature, that is 118 point minus 118.8 degrees centigrade, while the nitrogen is having the 147 0.1 degree centigrade, and the hydrogen is 240 degrees centigrade is to be there. So this is what the for the different gases the critical temperature is different. Now again, as the case where the all the critical points are all the critical point, the compressibility of the vapor is infinite, and density of the vapor and the liquid becomes equal. So this is what the stage where the critical point is to be there, where the state is going to be changing from the liquid from the gases to liquid, and where this is what some sort of middle point, where the density point is density becomes to be as an equal to be as an zero, we can say surface tension is to be zero at the stage, we can say. In the little bit next part maybe we will study that part where the density either liquid or the gases is going to be there, it is going to be equal, because it is the complete one stage where the gas is going to be converted into liquid, and that's what the quite interesting point where the critical point is to be there. And the distinction between the vapor and the liquid vanishes, both will be the same because it is at that mixing point is to be there. So this is all about the what the Andrews experiment is to be there. What we learned, very important factor, that is a critical point, the pressure or the temperature below which the gas is going to be converted into liquid, that is your critical temperature is to be there. At that whatever be the pressure, that is critical pressure is to be there. At that stage the volume whatever it may be, that is critical volume is to be there. Above the critical point or above the critical temperature, the gas cannot be liquefied, and that is what the importance of this critical temperature. Again, all the different types of the gases are having the different critical point, and according to the different gases behavior, they are whatever be the critical points are different. So this is what the first one Andrews experiment which shows that either the gas will not be in the gas state forever. With the change in the temperature and the pressure, particular temperature and the pressure, the gas is can also be converted into liquid is to be there. So this is what the final outputs from the Andrews experiment as far as on the CO2 gas is to be there. Thank you for joining this session. Again, be at home and be safe. Thank you.